We start recording. Okay, so we talked about last time we talked about dividing, multiplying, dividing radical expressions. And in particular, we started talking about rationalizing the denominator, and that's when you have a radical in the denominator. And we talked about this idea of conjugate, which is just the opposite sign of two terms, right? So if you have, for example, 3 minus radical 5, I want to rationalize the denominator, so I multiply by 3 plus radical 5 instead. And in doing so, I eliminate the radical from the denominator. So that's the idea behind multiplying by the conjugate, which helps us in dividing ultimately two numbers, right? We're dividing two numbers, but like I've maybe have mentioned it before, dividing is really just multiplication. The same way that subtracting is really just adding the negative of something. So we're going to continue on with radicals. And of course, right, we always talk about new things, simplifying new things. We talked about simplifying rational expressions, and then we end up solving rational equations. We talk about factoring trinomials, and then we end up solving quadratic equations. We end up simplifying radicals, and guess what? We're going to now be talking about solving radical equations. So these are going to be the equations where you have radicals in them. Okay? So let's see how we approach this. Okay, so we have a radical equation here. This is an example of a radical equation. The moment you see a radical in it, it's a radical equation. Now, what do we want to do? We want to isolate. So the first thing is isolate radical expression. So what does that entail to isolate a radical expression? Well, this is my radical expression, and I want to get it by itself. So what that entails is that I have to add the 6 on both sides to get it by itself. So when I do this, the rad x minus 2, that equals 6. And then once I isolate the radical expression, I need to exponentiate both sides. Exponentiate both sides of equation by appropriate power or exponent. So what is the appropriate power that I should raise everything here to? That's right, David. We want to square everything. Why do we want to square it? Because I want to get rid of that radical. To get rid of that square root, I square. So I square not just the left side, but I also square the right. So when I square the square root, they're inverses of one another. They're just the opposite. And so therefore I'm left with x minus 2. So the square root cancels. And then I get 36 squared, I get 36. And now look what I have. I have a simple linear single variable equation that I can solve. So I add by 2 on both sides, and I get that x equals 38. So I get one solution. Now I have to be careful though, always and forever. I need to check The same way I had to check for rational equations, right? Remember with the rational equations, we sometimes had extraneous roots that when we plugged it back into the original equation, it didn't actually work out. Uh, this can also happen in radical equations. So just check. Check if x equals 38 works. And for this one, it will work, but just check. So this is 38 minus 2. I'm plugging it in, right? When x equals 38, I'm plugging in 38 for x, and I want to see if the original equation does hold. So does the square root of 38 minus 2 minus 6, does that equal 0? Well, 38 minus 6 minus 2 is the square root of 36. And then the square root of 36 is 6. 6 minus 6 is 0. So yes, of course, this works out. Now, radical equations are not just bound to square roots, as we have seen, right? They have also, we can have different roots. We can have different radicals, different indices for the radical. So what if happens if I have the cube root instead of x minus 3 minus 2? So in this case, I still have a radical expression, don't I? This is my radical expression. I still want to get the radical expression alone. I want to isolate it. I don't want the minus 2 to be next to it on the same side of the equation. So I still have to do the same exact step, right? I add by 2 on both sides to get rid of the negative 2 on the left side of the equation. And so I get the cube root of x minus 3 equals positive 2. But of course, I'm not going to want the radical any longer. So I need to exponentiate both sides of the equation by the appropriate exponent. But in this case, I can't square it because squaring the cube root won't get rid of the cube root. But what would get rid of the cube root instead? What should I raise the cube root so that I can get rid of the cube root? Anybody?
We raise it by the third power.
Correct. Thank you. You cube it. So when I cube the cube root, I am undoing each other, right? They're inverses, they are inverse operations. The same way when you multiply and divide, right? If you multiply by 5, divide by 5, it cancels out. When you cube root something and then you cube it again, you undo what you just did. So you're left with x minus 3. You cancel them out, right? Some people like slashing them away. And then 2 cubed is what? 8. And now again, I have a very standard linear equation that I can easily solve if I add 3 on both sides of the equation and I get that x equals 11. That is my solution. And just in case there's no funny business going on, I always need to check what the solution that I get is, whether or not it actually works. So then I need to plug it back into my original equation. So this would be 11 minus 3 minus 2. Does this equal 0? That's the question. 11 minus 3 is 8. The cube root of 8 is 2. And so 2 minus 2 does indeed equal 0. Okay, so we checked it out. X equals 11 is indeed the solution. So hopefully start seeing the pattern of how this whole idea works, right? When we have radicals in our equations, we can find the solution. We just need to be a little bit more careful with how we solve, and we exponentiate with the appropriate exponent so that I can eliminate the radical and solve a very nice equation as so. But of course, we start, this is hopefully you start seeing the kind of, pattern, most likely, right? With the pattern that most of these kind of mathematics classes take, right? I teach you a new little topic. I show you like the first simple examples. And then of course, radical equations can get very complicated. It can. And I'll show you one of them. These are the simple ones when you have just one radical expression. But sadly to say, there might be situations where you have more than one. So what happens when I have something like so? Now, this is a bit more involved because we have two radicals. So now this is when you have radical equations with more than one radical expression. Radical equations with more than one radical expression. Okay? And the key phrase here is more than one. Um hmm. So the thing is, guys, you could do more than one way of doing this. There's more than one way of going about doing this. But what's suggested, what's recommended is to do the following. So I know in these examples here, I want to get radicals by itself, right? I can't do that because I have two radicals. So what I'm going to do is I'm going to put one radical on each side of the equation. So split up the radicals on separate, I should say on opposite sides of the equation. So I have radical 2x minus 1 plus rad x. So I want to subtract rad x on both sides so that I can do the first step. And then I get rad 2x minus 1 equals 2 minus rad x. The reason why I do that is that despite the fact that I have two different radicals, right? Look on the left side. On the left side, I have one single radical. Now, how do I get rid of, so we're going to do this step by step. How do I get rid of this radical? What must I do to get rid of the first radical on the left? If there was no extra radical, if it was just a 2, what would you do to this? What would you raise this to? What power?
The second power?
The second power. So that's what you would do, right? The thing is, we're going to do it on the both sides. Now, when I do that on the left side, when I square it on the left side, I'm left with 2x minus 1. That's awesome. But on the right side, I don't get rid of the radical just like that because of the 2 minus part. So actually, this side here, I have to multiply 2 minus rad x multiplied by 2 minus rad x. I have to square it and I have to FOIL. And if you guys know the squaring of a binomial, this is actually, there's actually a formula for this that we've discussed before, but it's okay. We can just distribute everything. And when we distribute everything, what do you get? You get 4 minus 2 rad x, and then the inner is minus 2 rad x again, and then the outer negative x times negative x becomes positive x, because square root of x times square root of x is x. Now look what we have. I can combine like terms. So you see everything that we just discussed before in the previous classes about multiplying radicals, right? It comes right back to this here. I'm multiplying radicals here again. So I got 4 minus 4 rad x, because they have the same same expression underneath the radical. So I can combine the coefficients, and I got plus x, 2x minus 1. So look what we have. I went from having 2 radicals to only having 1 radical. So I'm almost there. So what else do I need to do now? So I need to exponentiate, right? Both sides. By appropriate exponent. And then after that, I need to do what? I need to isolate the remaining radical. So the remaining radical is right here, radical x. So I want to get that on this, on just on its separate side. So what that means is I must subtract x, subtract x. I must subtract 4, subtract 4. So when I do that, the x's cancel and the 4's cancel, and I'm left with x minus 5 equals negative 4 rad x. And what do I do here? I want to get rid of the radical. I isolated the radical on the right side. So what must I do? Square again. I have to square again. So in this case, when you have more than one radical, you might have to exponentiate more than once. You're going to have to raise both sides by 2 twice. So I did that once in the beginning. It's my first time here. And now I do it again. And when I do so, what do I get on the left? X minus 5 squared is x minus 5 times x minus 5. And negative 4 rad x quantity squared, I take negative times a negative to positive. 4 times 4, or 4 squared, right? You can do this like this, right, as well. You can take this negative 4 and square it, take rad x and square it, right? That's another law of exponents. Negative 4 squared is 16. Rad x squared is just x. When you expand or FOIL x minus 5 and x minus 5, I get x squared minus 10x plus 25. And look what I get at the end. I get a quadratic equation. So in the simpler examples of solving radical equations, I got just a single linear equation. But now when we have double the radicals, I get a quadratic equation as a result. And I want to solve it. So I need to subtract 16x on both sides. So that I can set the equation equal to 0. And so I set my equation equal to 0. And now I have a trinomial equal to 0. And the question is, can I factor x squared minus 26x plus 25? Are there two numbers whose product is equal to positive 25, but when you add them, give you negative 26? So what are those two numbers? Anybody have the two numbers that multiply to 25 positive, but when you add them, give me negative 26? Negative 1 and negative 25. Very good, Sima. Yes, that's right. So this becomes x minus 1 and x minus 25. Negative 1 times negative 25, give me positive 25. Negative 1 plus negative 25, give me negative 26. So those are the correct two numbers. And then what do we do at this point here? We solve, right? X equals 1 and x equals 25. So apparently, I got two solutions for the original equation. But you always have to be, thank you, Kailani, thank you. You always have to be mindful, though, because the moment you square, like we just squared both times, right? But you have to be careful with that, because when you square something, it inherently, in a sense, it changes the equation. We changed the equation from having radicals to having squares in them. And so we have to be always careful, because even though we get two solutions, those two solutions pertain to the quadratic equation, not necessarily to the original radical equation. The quadratic equation came about because we're trying to solve a radical equation. So let's check. Let's check. So check. What happens when x equals 1? When x equals 1, I'm going to plug in, right? The square root of 2 times 1 minus 1 plus the square root of 1. Does this equal 2? Again, this is the original equation. 2 minus 1 is 1. The square root of 1 plus the square root of 1. Does that equal 2? Well, the square root of 1 is 1. And 1 plus 1 does equal 2. So x equals 1 works. That works. Now let's plug in 25, because that's the other apparent solution. When I do this, does this equal 2? Right? That's the original equation, right? So let's look at it. 2 times 25 is 50. And 50 minus 1 is square root of 49. Square root of 25 is already 5. Already you should notice, wait a minute, the numbers on the left side of the equation are way too big already. And I got 7 plus 5. Does 7 plus 5 equal 2? Absolutely not. So 7 plus 5 does not equal 2. So this x equals 25 must be rejected. Sorry. We must reject. Why? Because this solution that gives me nonsense. It doesn't give me the correct true equation that I started with. So this one does not work. So I have to reject it. So what's my solution? My solution is x equals 1. And only x equals 1 is the solution. It's not x equals 25. Okay, so whenever we have more than one radical expression, we have to do this double squaring sequence of steps. And then we have to be mindful of the solutions. Like there could be more than one. And just be careful with checking them to make sure that they satisfy the original equation, because that's what we really care about. We don't care about necessarily the quadratic that comes up, even though it's important to know how to solve it, how to factor it. But the solutions of the quadratic equation are not necessarily the same as the solutions for the original radical equation. So therefore, we have to check. Okay. Let's see. What else do we have? what about if we got something like this? Rad x minus 1 plus rad x plus 5. Pardon me, plus 4 equals 5. Two radical expressions. I want to solve it, so I must first separate them so that I can square one of them. So I'm going to put x plus 4 on the other side. So these cancel here. And I'm left with the square root of x minus 1. That equals 5 minus the square root of x plus 4. Okay? I must square both sides because I want to get rid of the radical on the left side first, and I get x minus 1 on the left side, but I have to be careful here because I'm taking the square root. I'm taking the square of 5 minus the square root of x plus 4. So what do? We multiply this, right? 5 times 5, and I get 25. And I get minus 5 rad x plus 4 minus 5 rad x plus 4. That's foiling, right? We're foiling. And then we do plus. What is the square root of x plus 4 multiplied by the square root of x plus 4? And of course, this combines, and I get 25 minus 10 rad x plus 4. So what is the square root of x plus 4? What is this? Times the square root of x plus 4. What happens when you take the square root of something and multiply by the square root of that same thing? Remember? So recall that the square root of x times the square root of x equals x. So the square root of x plus 4 times the square root of x plus 4 is exactly x plus 4. You can plug in anything. The square root of something times the square root of the same thing is that thing. So this is what I have. Now, the next thing we would do is what? Now that we have a single radical expression left, I want to get that by itself. So I have to move everything on the left side. And what happens though? What happens when you subtract x? They magically disappear. And then I'm gonna do what else? I'm gonna subtract the 4, and I'm gonna subtract the 25 as well. So -1 minus 4 minus 25 is what? -30 equals -10 rad x plus 4. Now I can square both sides, or I can be just a little more intelligent and say, hey, I can just divide a -10s. And when I divide a -10s, I get positive 3. That equals the square root of x plus 4. And now I can simply square both sides. And when I square both sides, I get 9 equals x plus 4 because I take the square root and I square that. And I subtract by 4 on both sides. And what do I get? I get 5 equals x, or in other words, x equals 5. All right. And now, of course, we want to check what? Our original equation. I get the square root of 5 minus 1 plus the square root of x plus 4. Does this equal 5? Well, what's 5 minus 1? 4. Square root of 4, and then, sorry, I should write this 5. 5 plus 4, that's the square root of 9. That equals 5. Well, the square root of 4 is 2. The square root of 9 is 3. And 2 plus 3 is 5. So, correct. Yes, that is true. And so this is indeed my solution, or my root, x equals 5. Okay? Any questions, guys, about solving radical equations? Okay. All right, let's do one more of these and then we can continue. So what happens if I got something like this? Can anybody, without solving it, can anybody tell me what x would be without solving it? And you can guess. Does anybody have an idea? If not, we can just go and try to figure it out. So let's add rad x plus 5 on both sides. -4, you say, David? Well, the moment you talk about negatives, right? So for example, if I plugged in -4 into x here, I'm going to be talking about square root of -4. And the square root of a negative number is no longer a real number. It's an imaginary number. So that's another whole world that we're not really going to be concerned with. But it might pop up in your subsequent math courses, especially if you're going to do anything related to engineering of any sort. I is equal to, or the imaginary unit is the square root of -1. But in this class, we're not going to be dealing with that. So -4 is a good idea, but it's not going to give you a real number. It's going to give you an imaginary number. If you plug in -4 in here, yes, -4 plus 5 is 1. Square root of 1 is 1. But the thing is here, you would have an imaginary number. So you have an imaginary number minus a real number. That won't equal 1. But that's
I see that, Professor. All right.
Yeah. Yeah, but that's a good idea though. Still, you thought about something that might work, but it doesn't, but that's okay. And we'll just go on and you start to see something. Hopefully, you start to see something. So this is what we have, right? After we add the radical expression. And then what do? We square both sides. So when we square the left side, what do we get? We get x. And look at the right side. We get 1 plus the square root of x plus 5. 1 plus the square root of x plus 5. Expand, I get 1 plus, and I get rad x plus 5 plus rad x plus 5 plus x plus 5, because rad x plus 5 times rad x plus 5 is x plus 5. And I get x here, right? And then the x is here. I want to combine the middle, pardon me, the outer and inner terms, and I get 1 plus 2 rad x plus 5 plus x plus 5. What so happens is when you subtract x on both sides, the x's cancel, And I also have minus 5 here, minus 5 here, minus 1, minus 1. So the minus 1s and the minus 5s cancel, and I'm left with negative 6 equals 2 times rad x plus 5. And then you can divide by 2 on both sides, and I get negative 3 equals rad x plus 5. And already there, I don't know if you guys see that already. There's a problem here. But let's say you don't see it. Let's say you square both sides like you're taught, like you're told to do. Negative 3 squared is positive 9, and this becomes x plus 5 because you square the square root. And you subtract by 5 on both sides, you get 4. X equals 4. And then you're like, yeah, that must be the answer because we get one solution. So, but when you check, what happens when you check? Again, you check with the original solution. So you get the square root of 4 minus the square root of 4 plus 5. Does this give me positive 1? What is the square root of 4? It's 2. What's the square root of 4 plus 5? 4 plus 5 is 9. The square root of 9 is 3. What is 2 minus 3? It does not equal 1. Wait a minute, what? Negative 1 does not equal 1. So what does that mean? Reject. X equals 4 is not a solution. So then, wait a minute, what is the solution to the original equation then? What's the conclusion? What's the conclusion, guys? If I found one solution, but that doesn't work, the only solution that I apparently have is not an actual solution. So we say, Jeremiah, very good. We say the conclusion is we have no solution. That can happen. We have an equation that has no solution to it because it doesn't make sense. I don't know now if you notice that it doesn't make sense from the very beginning. That's why I wanted to see if anybody caught it. If you look at this equation, you should already also, in a sense, know or be able to observe that this has no solution. Why wouldn't this have no solution? If you perceive the expressions a bit more, rad x, you're subtracting rad x with rad x plus 5. So what you're saying is you're taking any number, right? Choose a number. And then you're getting a bigger number, 5 units bigger. And you're taking the square root of each of those things and subtracting the bigger radical minus the smaller radical. Obviously, it will never be positive. So you can never have a result being positive 1 because your radical here is bigger than the radical that you start with. So if you're taking a number and you're subtracting a bigger number from it, you're going to get a negative number. So automatically, you should maybe have been able to perceive that there's no solution, but maybe you didn't, right? And then we get to this point here. I don't know if you guys remember this. We get to this scenario here where we get negative 3 equals rad x plus 5. You could have also perceived here or observed here that this also has no solution because there is no matter what x value you choose, I don't care what x value you choose, you'll never get a negative number when you take the radical of anything. The most you can do is get this I stuff, but we're not even dealing with I. So there's no possible way that a radical expression can produce a negative number. So make that a note. So note the radical expression. So again, this is only for square root. The square root function does not produce negative values. So it can never happen. So from here, you could have been like, nope, no matter what I do, it doesn't work. So this is a situation where we have no solution. Okay, so this is solving radical equations. And you might see, and you might ask, but why do we care? Why does this ever pop up? Well, square roots pop up a lot. And one of those cases is when you have what's called a right triangle. For example, let's say I have one side of it being 3, and I have the other side here, the long side being 5. And let's say I have a missing side. I'm going to call it B. Now, what is that famous theorem? I think we talked about it earlier. That relates the sides of a right triangle. What is that ancient theorem? Starts with the P. That connects the Pythagorean. That's right, Kailani. The Pythagorean theorem. This theorem you have heard time and time again. It's probably one of the few things that just seems to permeate through time. People just remember, oh yeah, the Pythagorean theorem is a squared plus b squared equals c squared. And it just seems to be true, right? Like it just ABCs, 1, 2, 3, just seems to make sense somehow. Now, what does the A and the B represent? It represents the legs, quote unquote, the legs of the right triangle. And when I mean by legs, I mean not the hypotenuse. And the C is the hypotenuse. And the hypotenuse is the longest side. It's the longest side of the right triangle. And so then you're like, wait, I can use this theorem and relate the sides of the right triangle together. So this is my B value, this is like my A value, and that's my C value, because that's the hypotenuse. And then I can replace each of those variables with the corresponding numbers. And so I got 3 squared plus B squared equals 5 squared. What is 3 squared? 9. What is B squared? B squared. What is 25 squared? 25. Subtract 9 on both sides. What do I have? I got B squared equals 16. I want to get B by itself, not B squared. So what must I do? Square root that thing. So a square root, radical appears. Radical B squared is just B. And rad 16 is 4. You have to be careful though, when you square root the square of a variable, you do get 2 numbers. You get plus or minus 4. So just keep a note on this, because this will appear again, especially when we talk about solving radical equations with square roots. So note, when you take the square root of x squared, for example, you really have plus or minus x. And then this is versus the square root of x. When you square it, you just get positive x. There is a slight difference with this. There is. So when you square something and then take the square root of it, it's different from taking the square root and then squaring it. And you can try this on your own. You can choose numbers like 9, for example, and you can see how this can give you two different answers. Okay, but of course, we're not going to use the negative. We're not going to use the -4 because we're dealing with length. So this is the length of a side. So it makes absolutely no sense to say, hey, this is -4 meters long. It doesn't make sense in this context. So we eliminate the negative and we say b must equal +4. So what does that mean? This is 3. And what I just showed you guys is an example of what's called the Pythagorean triple. What is a Pythagorean triple? It's a set of 3 numbers, a set of 3, usually they're whole numbers that all together satisfy the Pythagorean theorem. And so we have one of them, right? 3, 4, 5. 3 squared plus 4 squared equals 5 squared. Awesome. Now, are there more? And of course, the answer is yes. How can we get more Pythagorean triples? How can we generate more of them or find them? How can we find them? Well, one thing is once you have one triple, then you have an infinite number. So from here, 3, 4, 5, 3 squared plus 4 squared, that gives me, oh, what did I do? This should be 4. 3 squared plus 4 squared gives me 5 squared. That's true. Now, what if I double every number of the triple? What if I double it? So 3 times 2, 6. 4 times 2, 8. And 5 times 2 is 10. Guess what I just created or found? I found another Pythagorean triple. And then you might be like, but how come? Well, if you try it again and plug it into the Pythagorean theorem, it works out. 6 squared is what? 36. 8 squared is what? 64. And 36 plus 64, if you add them up, does indeed give me 100. So this works as well. What if I triple every number from the original Pythagorean triple? 3, 4, 5. I get what? I get 9, 12, 20, 15. This is another Pythagorean triple. How do I know? Well, if I square 9 and I square 12 and does this equal 15 squared? Well, 9 squared is 81. 12 squared is 144. And if you add it up, you do get 225, which is 15 squared. And this goes on forever and ever. So these are like your leaves or like the fruit that comes out. And this is from the stem or the root. So this is like the root Pythagorean triple. And then you just have an infinite number of numbers that just continue on. You can get an infinite number of triples and they all satisfy the Pythagorean theorem, which is pretty cool. But of course, this is not the only root. Now let me ask you guys, can anybody give me the missing number here? So I give you one side, 5. I give you the hypotenuse, 13. Can anybody tell me what is that missing number for this Pythagorean triple? 5 blank 13. What would that blank be? So what you have to do is 5 squared plus x squared equals 13 squared. What is 5 squared? 25. What is 13 squared? 169. Subtract 25 on both sides, and I get that x squared equals 144. What does x equal? The square root of 144, which is 12. So this is another Pythagorean triple, and of course you can just double everything and you get a new one, 10, 24, 26. That also works out, and you do this forever and ever, and you get more and more. So I'll give you just two more of these, and then you can check these out for yourself. 7, 24, 25. That's another Pythagorean root triple. You got 8, 15, 17. That's another one. And this goes on and on. 9, 40, 41. This also works. 11, 60, 61 also works. 12, 35, 37 also works. And this, again, this goes on forever and ever, not only vertically, but also horizontally. So all of these numbers here, all these triples satisfy the Pythagorean theorem. And this goes on forever to the right. You just double everything, triple everything, quadruple everything, quintuple everything, and you get more and more Pythagorean triples. I think that's pretty cool. Pretty neat. Alrighty, so I'll stop here.